Hello everyone, welcome to Chapter 18. This is our first part of the thermodynamics part of this, and we talked about enthalpy in Chapter 9 that was also included in this unit, and now we're going to talk about entropy and Gibbs free energy. And so there's quite a few things to go through this, so we have 5 parts to this lecture series. In the first part, the calculations we're going to be concerned with are going to be predicting the sign of the delta S. Delta S is the change in entropy. So just to remind you, when we first did kinetics, okay, kinetics told us how quickly something happens, but it didn't explain what was actually happening, and so the energy changes in a reaction are really what are driving a reaction and its progress. And so in the thermodynamics section, we're going to look at that and see the differences between the energy in the reactants and products and how that affects how the reaction will occur. So how spontaneous a reaction is depends on several things. If it's thermodynamically favorable, then it typically will be spontaneous. Now, when we think of the word spontaneous, we think of like immediately, okay? But that's not what it means in chemistry. In chemistry, spontaneity means that the reaction will go, but it has nothing to do with how fast or how slow that reaction occurs. If it's non-spontaneous, that means it's going to require energy input to be completed. If it's spontaneous, it means that there is enough free energy in the system that it will be thermodynamically favorable, okay? And so typically the products will have less potential energy when you get done, but it does not mean how fast it goes. For example, the formation of a diamond is from a diamond to graphite could be spontaneous, but it would take a long time, pretty much forever for us, because much longer than our lifetime. So if it's spontaneous, that means that it could be reversible. Often something happens that it's not reversible, I should say. Okay, so if you have a spontaneous reaction, it is going to proceed in only one direction, and that's why we'll have one arrow, not the double arrow like we have in equilibrium, because that's the whole point of that double arrow when we're looking at equilibrium, is that it's a reversible process. It's going back and forth until it reaches equilibrium. There is no reversibility in a spontaneous reaction, okay? It's just going to occur in one direction, and that is it. If it is spontaneous in one direction, that by definition means that it cannot be non-spontaneous in the opposite direction, so it will not occur. And the example that they're showing you here is that you can, if you sit a beautiful car out in the weather long enough, then it is going to rust. Okay, it will never spontaneously go back to being painted pretty again. Okay, so spontaneous means it's rusting. Non-spontaneous would be the reverse of that, which cannot happen. The reason that a spontaneous process occurs is because it releases energy from the system to the surroundings. Most spontaneous processes are going to occur from high energy to low energy. And so as you remember, that is exothermic. Okay, exothermic because it is going to give off energy. And we talked all about that in Chapter 9. But some spontaneous processes are going to proceed from low to high, okay, and they're endothermic. And we've been thinking before that endothermic means that it's not going to occur without us doing something, okay? So it's a little bit different way of thinking about the energy and how we change from that potential energy of the reactants and the products. So there's two factors that are going to determine whether that reaction is spontaneous. One is the change in enthalpy of the system, which we already learned about, and the other is the change of entropy. Okay, enthalpy we know is delta H, and it's the difference between all of the internal energy and the PV work energy of the reactants and the products. All right, and we learned how to calculate that by saying the energy of the products minus the energy of the reactants gives us that delta H. The entropy change, or delta S, okay, is the difference between the randomness of reactants and products. What does that mean? It means the less organized they are, okay, then the higher the entropy is going to be. And so the classic example of this is if you have a deck of cards and you throw them up in the air, okay, they are not going to stack in a nice little stack when they fall to the ground. They are going to be all over the place and they're going to be all mixed up, and you're going to have to spend a lot of time trying to put them back into order. And that's because entropy is always favored, because if it takes energy to arrange things. And so the lower the energy, the more entropy you have. So one thing you got to watch while we're doing this, okay? Enthalpy is in kilojoules per mole. And we see an exothermic reaction to have stronger bonds in the reactants, okay? More stable molecules are going to be in the products. So exothermic energy is released, your delta H is negative because you have decreased that amount of energy. So you have now less energy in your products than you did in your reactants. It's endothermic if the bonds in the products are weaker. And so endothermic, you have absorbed energy and you have a delta H that is positive. Okay, all this we've already talked about. The enthalpy change is favorable for exothermic reactions, and it's not favorable for endothermic reactions, okay? So entropy is based on the second law of thermodynamics, okay? And the entropy increases as the number of energetically equivalent ways of arranging the components increases. So that's a fancy way of saying that entropy is higher with things that have more parts to them that you could rearrange in different ways. So if you have a lot more atoms in something, it's going to have a higher entropy. Entropy, however, is in joules per mole. And remember, enthalpy is in kilojoules per mole. So you've got to watch that when you're working problems, because if you don't convert when you are doing the calculations, you'll be way off. All right, and entropy is defined as the Boltzmann constant times the natural log of W, which is the different ways you can rearrange something. Okay, so it's dependent on those two things. All right. Notice that Boltzmann constant depends on Kelvin. Okay, so temperature, and then how many ways you can rearrange something. Those are the things that are going to impact entropy. Random systems require less energy than ordered systems. If I want something to stay ordered together, I'm going to have to keep the energy coming to it. So the bottom line for this is, how far apart, how random are the molecules, okay? If I have a solid, it is nice and orderly, okay, in that solid, and they're all packed together real nice, okay? That solid is going to have lower entropy than the liquid version of that, because when I do the liquid, it's going to have more ways to separate and be apart, okay? The other way is, if that liquid, you take it and you heat it up and make it steam, then those water molecules are going to be even farther apart and more randomly moving, right? And so the gas is going to be higher entropy than the liquid. So the first law of thermodynamics says energy cannot be created or destroyed. So we saw that the energy of the universe must equal zero because the change in energy of the system equals the change in energy of the surroundings. That's our delta H. The total energy of the universe cannot change, but we can change it into form or we can move it around from one place to another. Okay, so that's our delta H part. The second law of thermodynamics says that the total entropy change of the universe must be positive if the process is going to be spontaneous. That is, the entropy must be positive if it's going to proceed in one direction. So in this case, the change in entropy of the universe equals the change in entropy of the system plus the change in entropy of the surroundings. For a reversible process, the change in delta S of the universe is going to be zero, just like we saw delta H. But if it's spontaneous or irreversible, only goes in one direction, we are going to increase the entropy of the universe. So the entropy of the universe is constantly increasing as we do spontaneous reactions. If the entropy of the system decreases, the entropy of the surroundings must increase by a larger amount because we're always going to get a higher change. And so that's why the entropy of the universe is always increasing. When the delta S, the change in entropy of the system, is negative, then the delta S of the surroundings must be positive. And so that will also mean that that is a spontaneous process. So the change in entropy is going to be equal to the entropy in the final, or the products, minus the entropy of the initial, or the reactants. Okay? Entropy change is going to be favorable when there is more randomness. Okay? That is that the delta S is going to be positive. Okay? And that means that your products are in a more random state. So solid to liquid or liquid to gas. Okay? That means that you're increasing entropy. A solid to a liquid to a gas. Whichever is more random state, okay? Because solids are more ordered or arranged than liquids, and liquids are more ordered or arranged than gases. And as I said before, the larger the number of molecules in the product, the more you have an increase in entropy. The higher you increase temperature, the higher you're going to increase entropy. Solids dissolving into ions, when you put a solid and dissolve it in water and make it aqueous and it turns into ions, that entropy is going to increase because you're spreading them out. So they're not going to be as arranged as they were when they were a solid. So basically what we're saying is that a solid has lower entropy than a liquid, which has lower entropy than a gas. And it's because of spacing and arrangement. And of course, it goes to say that as you're increasing temperature, you're changing from those states, from solid to a liquid to a gas. All right, so how does this apply? So we can predict just by looking at the components of a reaction if the change in entropy is going to be positive or negative. And so it's either if we're changing temperature or we're changing states or whatever. Okay, so in this one, we're going from a gas to a liquid. Okay, and so gases are less ordered than liquids. So when we get to the liquid, we'll have a decrease in the entropy, or a negative delta S. solid carbon dioxide sublimes, this is dry ice, right? And you see it wafting into a gas, right? It sublimes into gaseous carbon dioxide. So it's going from a solid directly to a gas. That's going to be an increase in entropy, right? Or a positive delta S, because that is going to go from a very ordered, organized situation as a solid to a much more randomly organized situation as the gas. And then finally in this one, okay, they're all gases, so I can't really go by changes in state. But what I can go by is the more molecules you have, or atoms or whatever, the more molecules typically in a reaction, the more disordered you have and the more ways you could rearrange those. So since I have 3 moles of gases on this side and 2 moles of gases on that side, I'm going to have a higher entropy on the side with the more moles, because I have different ways I could rearrange those. So whenever you have more of a component on one side than you do on the other, that's going to increase the entropy. So 2 moles going to 3 moles of gas. And so that would be a positive delta S. And remember, if we have a positive delta S, that is something that could be spontaneous. Doesn't have to be. We're going to find out later, but it could be. Okay. For these, though, we're going to just predict what the sign of the entropy change is. And then when we have numbers associated with it, it'll be the negative number or the positive number. But you've got to first be able to recognize what is going to have less entropy or more entropy. All right, and then I've given you one to practice on. And that's it for predicting the sign of the entropy.